feasibility of the installation of a microscale wind farm. Press the button if you need it.
Thank you.
Thank you.
Good evening, everyone. It's almost a mini abstract in itself, isn't it? But you know, when I got the title, I just thought that was the only one that really accurately described what I wanted to do. And so I want to go over what inspired me to do this and quickly go over some of the literature that exists in small wind turbine applications, much like what we might be wanting to do in Massachusetts. And then I'm going to go over kind of the broad scale, what equipment I was using and how I was going to go about this, and then how I went into the field and did it. And then look into the how I determined the economic feasibility of these turbines on our campus. Then the limitations, my results, and some ideas I've had for future research, if we have time. My inspiration was actually from an episode of Modern Marvels, where Jay Leno had installed a Pac-Wind Delta II vertical axis wind turbine on his garage, and he was actually producing power with that for his garage. And so I got into that and I was like, well, hey, if it's working good for Jay Leno, why not in all the other cities? Why not, on our campus? So I started looking into it, and there is actually the start of the movement began in the 1970s with the wind farmers of East 11th Street, where this was a group that put a wind turbine on top of their apartment building, and they went to court to get payment for the energy that they produced. The current research, though, is like what you said. It's very very broad. There's not much into actual wind flow through cities. You either have to go to it's either that very broad scale, or you have to go into very, very discrete, like street level data. So there's no in between. So and one of the things that's come about since then was during the election process, we had a call to arms for a new Manhattan project in alternative energy. And so this just kind of spurred me further. Maybe this could be something that could be part of that in the future. The equipment I used was very basic, just a GPS unit and the Kestrel 2500 NV weather meter, and along with the ArcGIS 9.3 software, which was available to me through the Northwest Missouri State Geography-Geology Department. Since this was during the fall and winter, I had to do a ground study to get a baseline for all of the data, as we needed to know the wind flow through the campus. And then also I needed to get out on the rooftops of some of the buildings in order to, well, if we're going to be putting the wind turbines on top of roofs, we need to know what the wind speed is up there. This is what I was thinking. And then I was going to use the data I collected and turn it into an interpolated map using ArcGIS. And just in case some of us have been asleep at the wheel for the last few years, interpolation is where you take a targeted point and then it's weighted, however further out you go is how much less weighted it is. This is a general map of the idea of interpolation. If you look over here in California, you see that you have this high value and then it fades off. That's interpolation, and that's what I was going to use for our campus. And then to generate ideas on how the feasibility of this project would go, I had to determine the potential at the marginal unit, the kilowatt hours. And to do this, I also needed to know how much these kilowatt hours would displace on the market their worth. So I needed to gather campus rates on campus electricity use and costs, and then kind of figure out what we could do with the energy. Could it be stored? Could we sell it back to a market like the farmers of East 11th Street? So how I went out in the field, I actually went out into the field and collected all this data. I'd stand out there, I had a clipboard in one hand, a GPS sitting on it, and the Kestrel like this. One would be blowing this way. And use the GPS to locate where I was going to go and time 2 minutes. And then I would just record and move on. It took me about 2.5 hours for these runs. And this was in cold winters of Missouri, so you had to be safe and wear lots of layers. And this is what I would put it into, an Excel spreadsheet. This is actually for the maps that we'll see here. This is January 7th, 2009. And what you see is I put it into a ratio just to give a general idea, data-wise, of what was going on. And then these first 9 points, since they're in a straight line, are considered my baseline. averaged them, and then that's where I got the ratio from, was comparing each individual average wind speed with the ratio of the baseline mountain. This is a map of all the points on our campus. I would start down here and just progress through the campus during that 2.5 hours. And this is one of the IDW interpolated distance weighting maps. This is the average wind speed on our campus. And as you can see, the most wind was over on this side of campus, so that gave me the where question of where to put these turbines in case we wanted to install them. And then just for reference, I have the gusts, and so you can see that this is what a day of westerly wind. So it penetrated much further than with the average wind speed. The rooftop data, though, as much as I wanted to get on the rooftops, it was inconclusive because I had scheduling conflicts, and Mother Nature didn't always cooperate, and which was a limitation which I'll talk about more later. What I was able to find, though, was that most of the rooftops on our campus were not able to have a straight wind. It was mysterious because I'd have to sit there and search for the wind like I had a dowling rod. So it could be the fact that maybe the rooftops aren't built in a way, or it could be the turbulence factor, which we face as a major problem to rooftop wind generation. One major equation I was able to find, though, is predicting wind speed at the heights. And this is velocity that you find that you're starting out with, and then the difference in the height that you're comparing. And this is the coefficient of roughness, and 0.3 is for urban or very heavily dense areas. And I just figured, go put it to the max and go from there. And that'll give you the estimated wind speed that you should be experiencing at that height. And I was nowhere near it during any of my testing. I think the best I got was about 50% of any of the V2 values that I computed. And the reason why this works is because over smooth terrain and rough terrain, you have a different rate of increase in the wind speed as you head up in the atmosphere. And as you can see, you go up a few hundred feet, you have only about 20% increase, but you already have most of the wind power already in place close to the ground over smooth terrain like rural farmland or a football field. But if you go over rough terrain like a city, you have very little wind at the bottom, and then you just go a little ways up, get that 60%. This is why the giant wind turbines are so far up, is to get above all of this ground clutter up here into the pure winds. So now look at the feasibility. And the basic question was, do these turbines pay for themselves? And one of the big things I had to figure out was the energy costs now versus later. So I had to do a little bit of figuring out, will we have energy increases that'll help pay for these? One major thing in this was that the wind speed of Maryville, Missouri, on average annually is 10 miles per hour, which classified us in a Class 2 wind. And this was thanks to the U.S. Climate Atlas, which I found through the National Weather Service. But the problem then becomes, how much energy do these turbines produce in a single month, year, and during their entire lifetime? And this is just a map of Missouri showing the general wind classes. And Maryville's up here, and we're surrounded by many Class 2 and then a few patches of Class 3. And Rockport, Missouri is over here as well. As you may have heard, it's the first city in the country to be